Okay, good morning, folks. This video is to go through part of the practical assessment, particularly the analysis and evaluation. Now, I'm going to share with you the brief on the screen. So here we have the brief, and if you see, all right, we're looking really at learning outcomes 3, 4, and 5. Okay, now when you're actually producing your results in the experiments, you've recorded them in a table. So 3.1 and 4.1 are essentially combined into one. So if you've collected sufficient and accurate data appropriate to the aims and objectives, and then presented them in appropriate format for analysis, then you've virtually fulfilled all of 3.1 and 4.1. I say virtually because as well as that, you also have to do the two graphs. So if we look at the 3.1, it says sufficient. Now, sufficient means that we've repeated it 3 times. Ideally, we should repeat it 5 times or even more. But given time constraints in schools and colleges, that's not really feasible. We also made sure that of the concentration, we had 5 different concentrations. And that's what allows us to give us a range of data. So in all, we'll have 15 sets of data so we can calculate averages and rates. Okay. Now, if I then go on to the actual results table. Here I've got a blank table. Here we've got the volume of the hydrogen peroxide in milliliters. You can use centimeters cubed, but you have to get to grips with superscript. Okay, that allows you to put the little numbers slightly above the, in the case of centimeters cubed, the cm. Over here, you can see on the rate of reaction, I have used the superscript button to get the -1 for the rate of reactions, which is seconds to the -1. Which in English would be written as per second. Now here, over on the top of the toolbar where my cursor arrow is pointing to the little X with a 2 above it, that's the superscript. Okay. Now in computer speak, it used to be called a toggle switch. So I have to turn it on to do the -1 and then turn it back off again. So I go back to it and turn it off so that I can then type normal size. Now, if you look at the concentration, I've gone to 1 decimal point here. In here, I would go to 2 decimal points. And if all of these are in decimal points, even if it was something like, so if I put in 5.40, I have to keep it as 5.40. Okay, so if the next one was 5.29, I've got to keep it to 2 decimal points, even if there's a 0 there. And again, if we had something like 5.07, then again, okay, we include those. And when we work out the average, okay, then we've got to make sure that we also put 2 decimal points, okay, and with the rate of reaction. Okay, notice that I've put in all of the units. So volume, milliliters, for concentration, molar. The readings, okay, we would put in seconds, average time in seconds, and the rate of reaction. If you look at then the graphs, here we've got the time taken in seconds and the concentration of hydrogen peroxide molar. Again, I would be expecting to see on those graphs the units, and then the actual graph itself. It looks something like this. Yours might be a straight line. Again, if we go over to the rate of reaction, we've got the substrate concentration, the peroxide. In this case, they've got percentage, but we'll have molar. And over here, the rate of reaction in seconds to the -1. And then we would plot our graph. Hopefully, it will curve. Now, when you come to analyze your data, you must use not only the figures here, but also the graph. So if I put some figures in here for 2 and 6, I'm not going to fill them all in, but say this was 31.33, 32.14 and 31.78, and then for 0.6, all right, as it's going slightly faster, okay, 19.87, 19.1, okay. Now, using this as an example, all of yours are going to be very, very different. Okay, what we would do is when we plot the average, we would look for any point that's off our nice line. And so if I look at this rate of reaction graph, which I got off the internet as an example, you can see here where it says 10.63. It's actually slightly depressed, it's down, where I would expect it to follow a curve here. Now, I can put a dotted line in there to join it up, and I would say, well, this particular result at 40, in this case it's percentage, but say this was 0.4 molar, then I can't turn around and I say, that's a possible anomalous result. And then I go and check, all right, the result. And if I could see that there was one result out, I would then comment on in my analysis and say, it's obviously that reading 2 or 3 at that concentration is slightly out. And that could be due to a number of factors, such as errors in making up these concentrations here when I was making the dilutions. It could be that the piece of cardboard was cut to a different size. It could be a timing error. So all of those are down to things like concentration, making up the dilutions, time recording, and cutting the piece of cardboard. Because remember, if you cut a piece of cardboard different sizes, you're increasing or decreasing the surface area. And that means that you will affect the reaction. And so all of those must be taken into account when you do your analysis. Now, you have to use the data from the table. So, for example, if I had the averages, I would put down something like at 0.2 molar hydrogen peroxide. The average time was, however, at 0.6 molar, the average time was. This shows that the reaction is getting quicker. If I compare the same concentrations for the rate of reaction, the rate of reaction was so many per second at 0.2 and so many per second at 0.6. This shows the rate of the reaction is increasing. This is confirmed by the two graphs, because on the average time graph, as the concentration increases, the time for the reaction to take place decreases, showing the reaction is getting faster. Whereas in the rate reaction, as concentration increases, it's a positive graph, and we can see that the rate of reaction increases. Now you need to link this to the theoretical context. So I'm going to take that down, and I'm going to go back to our assessment criteria, because it says, oh, sorry, let me just bring that back up. Okay, so here in 4.2, okay, it says draw conclusions for it, linking it to the theoretical context and the aims of the investigation. So all that work at the beginning of the assignment that we had to look at looking at the theoretical context now comes into play. We have to think about, so do these results fit the theoretical context, the theory behind enzyme reactions? And it's there, all right, that we would then, I'm just going to stop sharing so that you see me. So there, what you would do is you would look at your results and then fit it to the actual theory. So, for example, as the results show that the rate of reaction increases, this fits the theoretical context, because as the concentration increases, there are going to be more molecules within that solution. And there will be more molecules that have the minimum amount of activation energy. Activation energy is the kinetic energy needed for a successful reaction to occur as they collide. So if I have more molecules in there with the minimum amount of activation energy, you can see that therefore the reaction goes faster. So I produce more oxygen in a given time. Now that fits the theoretical context of our results. We would then look at, all right, our graphs and say, again, the theoretical context shows that as the concentration increases, so does the rate of reaction up to a maximum. Now, your graph may not show that maximum, okay, because it should flatten on what we call plateau. So it bends upwards and then goes straight. So you have a curve like that, and then it goes straight. Now that's the plateau. Now that point is called the saturation point. That's where the enzyme is so engaged with all the molecules that it can't possibly work any faster. It's reached its maximum rate, okay? Now, if your curve or line does not curve at the top, you can say that the researcher would need to increase the concentration of hydrogen peroxide beyond 1 molar. That would mean that you'd have to do another risk assessment, because if it goes over 1.5 molar, the hydrogen peroxide can cause problems if you get it on your skin or in your eyes, etc. However, you would increase it to show where the actual maximum rate, and therefore the constant saturation point, is on the graph. That is your analysis of the data, but you must use your data, your graphs, to explain that. When we move on to the evaluation, let's call back again the brief. Okay, when it comes to the evaluation, now I will have seen you carry out the investigation with due care and attention. You've still got all your fingers and eyes and things like that, so you must have done it with due care and diligence. So all of you will get that mark. So we've now done enough, okay, all right, to fit the theoretical context. And the aim of the investigation, which was, does the rate, does the concentration of hydrogen peroxide affect the rate of reaction? You can say it does, okay? It fits the theoretical context. It fits the aim that this variable will affect, okay, the actual rate of reaction. So you've proved your aim, okay? So we then go on to the last section, and you can combine these two together, 5.1 and 5.2, because it says describe the limitations of the investigation and describe improvements that could be made to that investigation. Now I would combine it because it's easier to keep a track of. So, for example, what's a limitation? Well, the limitations are, okay, the use of the measuring cylinder, which is only accurate, excuse me, to 0.5 of a mil, and that can be either above or below, so plus or minus 0.5 of a milliliter. That means when you make up your concentrations, they may not be as accurately made up as you think. So that's a limitation. So what you would do is then suggest an improvement. So the improvement would be to use a different type of measuring device for the volume. Now that can be either a burette or a graduated pipette. So that's a burette, B-U-R-E-T-T-E, or a graduated pipette, P-I-P-E-T-T-E. Those are much more accurate. They're around about 0.1 of a mil. In other words, they're 5 times more accurate than our measuring cylinder. So we minimize any complication from making up those concentrations. So you've spotted a limitation and you suggest an improvement. Now that's the pattern you need to follow to do 5.1 and 5.2. Okay, so I'm going to take the share off and go back to the screen. Okay, so the next type of limitation would be our pieces of cardboard. So although we proved our aim, again, it's a little bit quirky. Scientists don't like any problems with accuracy. So the cardboard, because we're not cutting it exactly the same size, that will give a variation in the surface area, and it will give another variable, which is that you're soaking up more of the celery juice, and therefore you you can't know if you've got more celery juice and therefore more catalase in that piece of cardboard than another piece of cardboard. Now, the surface area, okay, if that's your piece of cardboard, okay, and what, I know it's exaggerated, but then another piece of cardboard was this big, the surface area in which the cardboard reacts with the hydrogen peroxide differs from, say, that size to this size, and so therefore that's why it can affect the reaction. How do we solve that? Well, an improvement would be to use a hole punch to accurately cut out a piece of card. Okay, not wholly an improvement, because remember that the surface, all right, although we think things are nice and smooth, it's going to be all ridged and bobbly. So therefore, again, the cardboard surface. We could buy commercially available pieces of card that are cut. An alternative is to abandon the card and use a method where we collect the actual volume of oxygen. Now, to do that, we would need to use an inverted measuring cylinder. So we would get the measuring cylinder, turn it upside down. Look this up on the internet, the inverted measuring cylinder method for collecting oxygen gas. And you'll see a diagram on there that you could incorporate. An even more accurate way of doing this is to use a gas syringe. Looks like a very large syringe, but made of glass. Okay, it's about this diameter. This is a precision instrument, and we will connect it up to our equipment, and when the gas is produced, it would push the syringe out, and we'd have a scale in which we would be able to measure the amount of oxygen gas. Now, that is the all-singing, all-dancing way of improving our measurement of the volume of gas, instead of waiting for a piece of cardboard to float. Okay. Other things that we could try is the fact that we don't know exactly the concentration of the enzyme. That could vary between samples and how much is soaked up. So we could actually get commercially bought pure catalase, make up a solution and use that more accurately, all right, with the hydrogen peroxide, so that we would get less variables in our experiment. Okay, timing can be an error. Okay, also we didn't control the actual temperature. We assumed that because we were in the laboratory that it would always be the same temperature, but it's open to question because we don't know, was there heat generated in the actual experiment? Were there fluctuations in the room temperature? So again, what we would do to improve that is we would immerse our test tubes into water baths. Now, the water baths can then be thermostatically controlled, so we could set it at, say, 30 degrees, and we could monitor the effect of concentration on the experiment. Okay, so that's the analysis and the evaluation. Okay, make use of your data, fit it to the theoretical context. Does it prove your aim and your hypothesis that the concentration, as it increases, so does the rate of reaction? Then do the evaluation of the actual procedure. What were the limitations that you spotted? what were the improvements that you could have made. If there are any errors, point these out. And the solution to errors, remember, is to repeat those particular set of results. Okay, hope that helps, and I shall see you in class soon.